Finish 2.1, so properties, first of all. Okay, so properties of matrix algebra. So number one, so commutative property. So when we add matrices, can we add them both ways and get the same answer? What do you think? Yes. Right, because how do you add matrices? You add the corresponding entries, so 5 plus 2 is the same as 2 plus 5, so that is, it's commutative. So commutative under addition. But what about multiplication? No, and we showed that last class. In fact, you can't always multiply both ways because of the size won't match. So it's not commutative. So let's say in general, and I say in general, which means there would be exceptions to that. If you multiply something by 1, or the identity matrix, you do get itself. And if you flip that around, if they both happen to be square matrices, it would work both ways. So sometimes you could get them to be commutative, but in general they're not. You can't just flip the matrices around. Number 2, A plus B plus C is the same as A plus B plus C, where the order that we add is different. And that's called the associative property. So it's associative under addition. And it's also associative under multiplication. So if we did like A times B and then multiplied it by C, would give us the same as A times B times C. Okay, as long as we don't change the order of A, B, and C. So for example, A times B times C would not be equal to C times A times B. Okay, so take a look at that. So if you're multiplying something in front of C, C is at the end, you can't flip that around. Even if the size works, you won't get the right answer if you multiply them in the wrong order. So the order is very important that you multiply. Okay, so you can't change the order, but as long as they stay A, B, C, in whatever order it asked you, you can multiply the second two first, it doesn't matter. Number 3, A plus the 0 matrix, or vector. And I just put a little vector sign on there. It's like, just to say it's all zeros, right? Not just the number 0, but an actual matrix of whatever size we're talking about. If it all has zeros, so a 0 matrix. Same size as A. The same size because you can only add vectors and matrices that are the same size, so it would have to be the same size. You can multiply it in either order, or add, sorry, in either order and still get A. So adding 0 to something. And so this is called the additive identity. When you add something and get itself as the answer. And the multiplicative identity And remember what I stood for? It's a square matrix with ones down the main diagonal and zeros everywhere else. So let's look at an example. If I had A was 1, 2, 3, 4, 5, 6. So the size of A is 2 by 3. If I wanted to show A times I, we know it's equal to A, but if I wanted to actually write the two matrices out, what would they look like? So A is 1, 2, 3, 4, 5, 6. And what would I look like? It would have to be a 3 by 3. Why is that?
A is 2 by 3, and I have to be a square matrix.
Right, this middle number has to match, and I is always square, so I would have to be a 3 by 3. So I would look like 1, 0, 0, 0, 1, 0, 0, 0, 1. And if you multiply that, you get 1, 2, 3, 4, 5, 6. You get back to A. Now what if I put the I in front of the A?
That would be a 2 by 2.
Right, so now A is a 2 by 3. So the middle numbers have to match up, so that would have to be a 2. And since it's squared, it has to be 2 by 2. So this multiplication would look like and when you multiply, you would get 1, 2, 3, 4, 5, 6. Remember, the result is this size, 2 by 3. And the result, 2 by 3. Okay, so when you see A times I or I times A, I doesn't have to be given, it's the size that works. Okay, so that's understood to be whatever size would work to multiply. And you don't actually ever have to show that unless it asks you to, because if I said find A times B times I times C, what do you think that would be equal to? ABC. The I is like multiplying by 1. It doesn't really matter where it is. It's the size that works in the middle of those. So this would be ABC. You don't really need to do much with it. Okay, so property 4. A plus a minus A is equal to, it's the same as A minus A, so that would be 0. We'll put a little arrow on to say the 0 matrix. So back here, when you add two matrices and get itself, that's called the additive identity. Or when you multiply two matrices and get itself, that's the multiplicative identity, or just the identity. Usually we just say identity. So if you're talking about the identity, you're usually talking about the multiplicative identity, okay? Ready? Here, this is called the additive inverse, which is when you add two matrices and get the identity. And this works the same as in real numbers. The additive inverse for a number, 5, would be minus 5. It's whatever you add to give 0. Multiplication gives us, so the symbol is a little minus 1 as I's already used. So inverse, the symbol is actually a minus 1 on the A. And this gives us I. So A inverse is called, or A minus 1 is called the or just inverse. So when you say, when the question says find the inverse, they're talking about this, the multiplicative inverse. And we're going to learn how to find the inverse later, because there's a whole chapter on that. So that is the matrix that you multiply to get 1. So in real numbers, what would that look like? If I had 5, what would you multiply by 5 to get 1? 1 over 5. So that would be your multiplicative inverse in real numbers, or couldn't we say 5 to the minus 1? Right. In real numbers, it's like dividing by a number. There's no such thing as dividing in matrices, okay? So there is a technique to find that matrix of numbers that when you multiply you get 1, or the identity, okay? So we'll figure that out. But it does have an equivalent in real numbers, similar. So you can think of it as like the dividing matrix, but don't ever say divide, because we don't divide matrices. Now, so A times A inverse is equal to I, and it will actually work both ways. So what does that say about A and A inverse? If you can always multiply both ways. So in general, A times B does not equal B times A, because why? There's one huge reason why. If they're not square, the size won't match up when you reverse the A and B, right? So in general, when we say like A times B is not equal to B times A, well, that doesn't work a lot, because if this was a 2 by 3, and this was, say, a 3 by 2, it might work, but say it's a 3 by 1 or something, right? A 3 by 2 would have actually worked both ways. Then this is 3 by 1, and this is 2 by 3. So first of all, they won't work. What will always work? A square matrix, right? A square matrix, when you multiply by another square matrix of the same size, will always be able to multiply the other way. It won't always give you the same answer unless they are the inverse of each other. So if we have two matrices that when you multiply them both ways and you get I, so if you had A times B equals I, then you would say B is the inverse of A. Or A is the inverse of B. They're inverses of each other. Would you agree with that? So they're inverses of each other, and they're also square matrices. So we're going to figure that out later, but basically if you are asked to find an inverse, it's of a square matrix only. There's no such thing as an inverse of any other matrix unless it's square. Okay? So it's just a rule. just more on that note, like, even, say we multiplied two matrices that were not square, these can multiply both ways. Right, so you can have matrices that multiply both ways, but you won't get the identity. Okay, that just, it's not possible, it won't work. Okay, 5. Okay, so the next property is a scalar multiplication property. So if you had two scalars, you can multiply them into the matrix first, and you can save them both for later. You can put them in the same order, you can reverse them, it doesn't matter. Okay, so this is just saying that. So that goes for, when I gave this example in vectors, I said if you had like a fraction all through the vector, you could factor it out to the front and save it for later. That would go the same here, okay? 6. So if we had two matrices that you wanted to add together, and then a scalar you want to multiply by that, you could multiply the scalar by each. Distributive property works. You could multiply them first into each one, or later into the answer of the addition. So you could add first and then multiply by the scalar, or multiply the scalar separately. And that distributive property also works. So these are three matrices. So if we say the distributive property works, what you have to be really careful of is the order of the matrices, what order they're in. So here, A comes first. So if we multiply that out, this would be A times C. C has to be second, because A was first. And then this is plus B times C. So what I'm saying is you cannot write C times A. It has to be in the order that you see them. So A is first, so these are in the wrong order. Okay? So how would you distribute this C into this bracket? CA plus CB. The C is first. So this would be CA plus CB. So you have to be careful of that, okay? Because that is different than real numbers. When we do real numbers, it wouldn't matter what order you multiplied the two in. You could say it's 2x or x times 2, and that's the same thing. But in matrices, order is important. Okay, so to finish up this chapter, we'll do an example with some different questions in it. So I'm going to write some matrices down. Okay, so, you have that all written down? I'll rewrite the question and the matrices as we need them, but move that up. Okay, so solutions. All right, ABC. So the first thing I would do when you see something like this is check to make sure that the size will work, because otherwise the answer is no solution and you don't need to do anything. So how do we check the size? We would write the size for A, B, and C. So A is what size? 2 by 2. B is a 2 by 3. And C is a 3 by 1. So what are we looking for when we're seeing if this whole thing will work? We want to check the sizes that touch each other, so the middle sizes. So these size match, right? And do these size match? Yeah. What do you think the answer will be? What size? Yeah, the answer will be a 2 by 1. Which is how many entries? 2 times 1. 2. She's going to have 2 numbers in the whole answer for this. Okay. So where do we start with? The order is important. So you have to start A, B, then C in that order. You don't want to do it in backwards or something. You want to keep it in that order. So let's do A times B first. And then we'll multiply that answer by C, and we have to put C at the end of it once we get the answer. Okay, so we'll do this first. You can't multiply all 3 at the same time, so you have to go in 2 and then by whatever is next. So if you remember how to do this from last class, we're going to do dot products. So I'll circle the first one. So you start with row 1, and then you go through each column, keeping with row 1 until you're done all the columns. So the first dot product will be 1 times 1 plus 2 times 2. So that, will, whatever that is the answer. So 1 plus 4, 5. So staying with row 1 until you're done. So the next dot product is with C2. So 1 times 0. And I'm still in row 1 because I'm still on row 1 here. So 1 times 0 and 2 times 1. So 0 plus 2, it's 2. And staying on row 1 until I'm done with every column. So the next one, 1 times 1 plus 2 times negative 1. So it'll be 1 minus 2 or negative 1. So now I have no more columns to go through with row 1, so now I go to row 2. And that will fill in row 2 of my answer. So row 2 is here. And then I'll circulate through. Row 2 with column 1 will be 2 times 1 plus minus 1 times 2, 0. 2 times 0 and minus 1 times 1. And the last one, 2 times 1 and minus 1 times minus 1. So that's 2 plus 1 is 3. So this is A times B, not B times A, it's A times B. Now we wanted to find A times B times C, so we now have A times B, sort of like that. 5, 2, minus 1, 0, minus 1, 3, and we now multiply that by C. So this result was a 2 by 3, and that's a 3 by 1. So we've got 2 rows to go through, but only 1 column. So we say row 1 first. 5 times 2, 2 times 3, plus negative 1 times 5. So that's 10 plus 6 minus 5, so 11. Now I'm done with row 1, because there's no more columns. So that means you're done with row 1. There's nothing else in the answer for row 1 because there was only one calculation for row 1. So it looks like that. So row 1, there was only one column for that, so that's it. Now row 2 will be row 2 of your answer. So row 2 with column 1. Three times 5. So that's 0 minus 3 plus 15. So 12. And that would be your answer. So A times B times C is equal to 11, 12. Now, could we have calculated this in a different way and got the same answer? Yes. What way would that be? BC, and then take the answer for that and put A in front of it and multiply A times BC. Because one of our properties said you can do this as long as A, B, and C are in the same order. So you could find BC first and then put A in front of it and multiply. I wouldn't suggest doing that because then you usually would want to just put A second after you found that answer, and you could then say there's no answer, which I've seen people do before. Generally, you would just do it in whatever order it says. Don't try to be fancy, okay? All right, number 2 says what? This is the most common mistake here. So what you want to do for A squared is maybe square everything in A, but that would not be correct. What does A squared mean? A times A. Sometimes you can't even do A squared if the size does not match up. A happens to be a 2 by 2. Can we find A squared? Yes, because they match up. So A, 1, 2, 2 minus 1 times A. Now let's see if you could have actually squared each of the terms and had the right answer. So what do we do for this? Go with row 1 and circulate through our columns. So row 1 with column 1. 1 times 1 plus 2 times 2. 5. Could you have just squared that first term? No. 1 squared is not 5. So, all right, staying with row 1 until we finish. So column 2. So we're still in row 1. So 1 times 2 plus 2 times negative 1. 0. And then go on to row 2 with column 1. 2 times 1 minus 1 times 2, 0. And the last one, 2 times 2 plus a minus 1 times minus 1. 4 plus 1, 5. Interesting. What's that sort of look like? The identity, right? That's the right name. We can factor out a 5. So the answer to this is 5i, if you wanted. That would be an okay way to say it. You wouldn't probably bother with that, but if I said show that A squared is equal to 5i, then this is exactly what you would do. Okay, so that would be an alternate question. So the question could say, show that A squared equals 5i, and that would be the question, and all you'd be given is A. So you would multiply A times A, just like we did. Does that make sense? Right now it does, but if I put that on the test, everyone would be texting me and saying, what do you mean by that? Lots of people ask what explain means, which I kind of laughed, but it just meant do the work. Like, don't just write the answer, is what I meant by that. So just so you know in the future. which I answered most people by saying that. What you just showed me is right. That is explaining. So I didn't need a paragraph. I just say explain when I don't want you just to say they're parallel and then not show why they're parallel, right? They're parallel because they're a multiple of each other, or because A equals 2B, something like that. That would all be explaining, but just saying they're parallel isn't explaining. Okay. So what about B squared? Yeah, so B is a 2 by 3 matrix. So B squared would be B times B, which is a 2 by 3 times a 2 by 3. These are not equal, therefore B squared is not possible. And that would be explaining. All right, so you show that the size doesn't equal, so that's why they're not possible. What was 4? Where's my question gone? Okay, 4. 1/2 A times D. So 1/2 would be a scalar, so they're saying multiply 1/2 times everything in A and then multiply it by D. So we could do it that way. So 1/2 A times D. Oh, and before I wrote this out, I would check to make sure you can multiply A times D, instead of even writing it out first. But I did check, but I forgot to say that. I looked back and saw that A and D were both 2 by 2, so I knew I could multiply them. All right, so do we have to do it in this order that it's asking? No, remember a scalar multiple can be saved for later, or you can put it in now. I would personally probably save it for later where it's a fraction, and putting a fraction in and then multiplying with a fraction. I would just save the 1/2 for later and find A times D. So I would probably rewrite this myself as 1/2 A times D. Do A times D first and then multiply by 1/2. But you don't need to do that, okay? You could just multiply everything by 1/2. I'm just going to write that down, but it's not necessary, and I'm going to do it my way, but if you did it the other way, you should get the same answer. So 1/2 A times D. So first, forget about the 1/2 for a minute, and I'm just going to find A times D. Oops. So once I find A times D, then I'll put the 1/2 back in front and find that answer. So 1 times 3 plus 2 times 4. 8, 11. Staying with row 1, 1 times 2 plus 2 times minus 5 is negative 8. And now I'm done with row 1 because there's no more columns, so I go on to row 2. And that will form row 2. So 2 times 3 minus 1 times 4 is 6 minus 4, 2. And the last one, 2 times 2 and minus 1 times minus 5. So 4 plus 5 is 9. So that's A times D in the right order. And then we wanted 1/2 A times D. Multiply 1/2 by each term. Now, like I said, you could do 1/2 times A and then take that result and multiply it by D. Now, if you did reverse the A and D, it would work, but you wouldn't get the same answer. So you'd have the wrong answer. 5. check the size. E is what size? Oh, they're all 2 by 2, so it'll work. What wouldn't work? If A and D were not the same size, you can't add them, so that wouldn't work. And then E has to match up with the size of the result of that for it to work, but they're all 2 by 2, so the size is okay. To add two matrices, they have to be the same size. Now, we could do this, we could do E times A plus E times D in that order, not messing it around, but then that's 2 multiplications instead of 1. So, in this case, I would add first, and then do the 1 multiplication by putting E in front. And you have to make sure you put E in front, because it will work both ways. So A plus D first. Cool. Oh, you remember how to add. I got thinking about something unrelated to math. So 1 plus 3, 2 plus 2, 2 plus 4, and minus 1, minus 5. Sometimes when you're doing something boring, I've taught this lots of times too, right? So I actually started daydreaming as I was doing it. Just check my answer there. Now what do we do? Multiply by E, but be careful because E was in front. You have to put it in front. So you have to do E times A plus D. So E is 1, 1, 1, 1. Yeah, so is that just going to give us the same thing back? No, because it's not 1's down the diagonal and 0's everywhere else. This isn't multiplying by 1. So 1 times 4 plus 1 times 6, 10. 1 times 4 plus 1 times minus 6 is minus 2. Second row, same thing as the first one. So this is not because it was 1, 1, but it was because the first row was the same as the second row. Anytime the first row is the same as the second row, you're going to get the same answers. This could be 5 and 100. You would get whatever your answers are for the first row, and if this was also 5 and 100, you'd have the same answer for your second row. Okay. That's number 5. Number 6 says what? B, C, and C, B. Did we do one of these already? No. Okay, so B times C. B is size 2 by 3, and C is size 3 by 1. So that will work. We can do that. What about this one? 3 by 1 and a 2 by 3. So this one, not equal, therefore not possible. So that's that one. B times C we can find. B and C. So I'm pausing, hoping that you're just trying it yourself and see if you get the same answer as me. So 1 times 2 plus 0 times 3 plus 1 times 5. So 3 numbers, which will give me 2 plus 0 plus 5, 7. Second row, 2 times 2 plus 1 times 3 plus a minus 1 times 5. 4 plus 3 minus 5 is 2. And this is a 2 by 3 and a 3 by 1, so the answer should be a 2 by 1, and it is. So just to double check that you put your numbers in the right order. So there's B times C and C times B, and then I ask the same thing for A and D. So A and D are the same size. So they'll both work. All right, so we're going to get an answer for that. This is A times D, and then we'll do D times A. So 1 times 3 plus 2 times 4. 1 times 2 plus 2 times minus 5. I'm just going to do it quickly to get the answer, and you can try it later. Two minus 10 is minus 8. 6 minus 4 is 2, and 4 plus 5 is 9. All right, so 3 and 4, 7, 4, minus 6, 13. So, I mean, why did I ask this one? To show they're not equal. All right, so A times D is not equal to D times A. Can that ever happen that they are equal? Is there any possibility in the world that I could find that you multiply A or two matrices both ways and actually get the same answer? Yes, if they are inverses of each other. Inverses will give the identity either way. All right, that's the only ones. If they're inverses of each other, which we'll do, and I'm guessing it's the next section, but I forget. I'll have to grab my notes. So that's it for 2.1. So I'm going to stop the video, and we'll start 2.2.